Okay. So I think let's get started here. So today we're going to talk about GANs, but before we get started, I was wondering if people had more questions or if we can run a little bit of review from the lecture on Tuesday. If people had questions, comments, or concerns about like this idea of like a latent space and like a codebook representation of inputs. If not, I'll do a quick review of it anyway. But if there's pressing questions, that's probably slightly more pressing than the back half of this lecture, which is going to be far less crucial and critical. So if people have questions, I'm happy to take them. Here. All right. So yeah. So we're going to talk today, if not about GANs, we're going to go over first a little bit some stuff that we talked about on Tuesday. So this is a review, but again, please feel free to stop me if there's any questions or comments or concerns about what I'm saying. So on Tuesday, we talked about latent variables and this idea of like codes. Like we have a whole bunch of different inputs in like an image data set, and we want to figure out how to compress them and map images into more compressed representations in the form of like say a 32-dimensional vector. So we have a 128 by 128 image. The challenge in the case of like an autoencoder is to figure out how we can represent that 128 by 128 image with simply just like a 32-dimensional vector. Like how can we encode all of the important information that is in an image and put that into a vector that then we will pass to a decoder who is responsible for looking at that vector and saying, okay, based on this vector, I know what was in the input image. I know what the most important parts were, and I'm going to try my best to reconstruct that. And if we want to, we can, after we're done training an autoencoder on this setup of just a giant data set of unlabeled images, we can generate new images if we want by just sampling new latent vectors that maybe we didn't get while training on our data set. And if our decoder is working well, hopefully it will be able to attempt to, or it will attempt to decode that into something that looks good and realistic for our data set. So that was sort of the key idea that we wanted you to take away from like Tuesday. Yeah, were there questions or comments on that? All right. So the thing that we were really looking for from like our autoencoders is we really wanted things that look like in distribution for our data, which means, so given like a data set of like cats or dogs, we're hoping that our generator will generate an image that looks like a cat or a dog, and like a real cat or a dog too, not like a stick figure or something lame. But how do we like judge this? Because this is sort of a really subjective thing. Like how do we know when our data looks good? What does good mean? So if our data is something really super high dimensional, like an image, 128 pixels by 128 pixels by 3 color channels, that's like a lot of different choices we can make at every single pixel. And this can be really difficult to figure out, like, given this really complex input, what does it mean to be good? What does it mean to be like realistic? And oftentimes you don't really have enough data to form like a real probability distribution. So it's really hard to kind of figure this out. How do we figure out whether something is outputting according to our data distribution or not? Sort of this weird nebulous concept that we're trying to solve. And rather than trying to solve this directly by hand specifying what defines a good looking image, this is deep learning. We're just going to have another network try and judge how realistic our outputs are for us. And that brings us into what GANs are in the GAN game. Are there questions so far? All right. So the core idea is that we're going to have two networks that are competing against each other. One is trying to generate data, and the other one is trying to guess whether that data looks real or it looks fake. This is sort of a game theory-esque concept. The discriminator wins this game when it has low loss, when it's classifying images correctly as real or whether they're fake. And the generator gets really low loss when it fools the discriminator and gets the discriminator, convinces it to classify its outputs as real images. So they're competing against each other. So your discriminator network is going to take in a batch of fake images and a batch of real images and try and figure out which ones are real, which ones are fake, try and divide them up if it can. And the generator, again, is just responsible for feeding the fake images and trying to get better and better results according to your discriminator network. And because everything here is still fully differentiable, all of our linear layers, convolutions, all of it's still entirely differentiable. We can still backpropagate all the way through from our discriminator's output, from the classification that it does, all the way back to our generator's weights. So we can still run gradient descent and all of that. But yeah, that is the high level for GANs here. It is effectively this game theory, this game that these two networks are going to be playing, competing against one another. And you'll notice it's sort of a slight shift from autoencoders. Whereas autoencoders were trying to take inputs, represent them in a compressed way, and then decompress them. Instead of the bottleneck being in the middle, we have something in the middle between these the discriminator and generator networks. That's a lot more high dimensional. It's sort of like we just swapped the discriminator or the encoder and decoder from our autoencoder setup. And it's a slight paradigm shift. The difference is, whereas in autoencoders we're training jointly, the encoder and the decoder were working together to try and best reconstruct images. With GANs, our discriminator and generator network are competing against one another. But other than that, the same techniques, the same architectures you use for your encoder and decoder will work exactly the same for your discriminator and your generator, respectively. So it's not a terribly large conceptual jump, or a jump in terms of what you need to actually go and implement. Yeah, that's what I want you to take away. So the things we have agency to choose. Oh, and I should note as well, the input to the generator is going to be just some kind of random noise vector sampled from some multivariate Gaussian or something like that. It's just going to be some random noise that the generator is then going to try and figure out, okay, like, how can I assign some meaning to this random noise so that I'm not always outputting the same thing every time? Because if your generator outputs the exact same image every single time, your discriminator is always going to win. It's going to say, I've seen this image before. And it's always going to tell for certain that an image is fake. So we need to give it some source of randomness, something to try and, again, assign random meaning to. The generator is going to see this latent variable of noise and just try and decide, okay, if this value is big, that means my cat is going to be standing up or running or something like that. It's going to get this variable, this latent variable of just noise, and try and assign meaning to it so that it can generate a whole host of inputs, or a whole host of real looking images. So we have agency to choose how big the latent vector is and what distribution we're going to sample from. We can choose the generator architecture that goes from just a single variable, latent variable, just a vector, all the way up to something that looks like an image. It should have the same size, the same shape as our real data. We can also, we also get to choose like the discriminator as well. This is a typo, I apologize. The discriminator architecture that goes from either real data or fake data, all the way down to like a value between 0 or 1 that classifies how much we think it looks real or fake. And then like the loss functions we're using, hyperparameter optimization, all that. So those are the things that we have agency to choose when training a GAN. So this is sort of layman's terms. Hopefully don't worry too much about the math on the right. If you want to go back, look at it later, that's fine. But for now, the thing I want you to care about is that on each batch of real data, for the number of times that you want to update the discriminator's weights for this real batch of data, we're going to take all of our real data, and we're going to also generate some fake data. Pass that to the discriminator, and then choose to update just the discriminator's weights. And then alternate back and forth between training the generator, the discriminator, the generator, the discriminator, giving them each a turn to improve before going back and forth. And you can choose whether you want to update the generator multiple times before you update the discriminator, or vice versa. So these are some things in the training procedure that we also have a little bit of agency to choose. But again, the core thing I want you to take away is when you're training a GAN, you simply just alternate back and forth between the generator and the discriminator, just doing gradient descent, freezing the other one's weights. Yeah. Are there questions so far on GANs or this idea, training procedure? Yes, friend. Yeah. 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 Well, so it's basically like, it's really, again, like going back to the very start, like it's really hard to figure out like what makes an image look like realistic. So we're just gonna have like a network that's given a whole bunch of real data and fake data. And yeah, if the generator does its job and is able to start trying to figure out some patterns of like what makes our image look fake, like how can I tell that this image that I've gotten is clearly fake as opposed to like real, then our generator will get some feedback. It can tell based on what the generator is deciding, like why the generator made the decision as to whether the image looked real or fake. Our generator will start getting like feedback. We can propagate our gradients all the way back into our generator, and our generator can see like, okay, the discriminator knows that this color scheme that I've been outputting is clearly like fake. I need to change this a little bit. Does that make a little bit of sense? Yeah. It wants to fool it. Exactly. And the discriminator starts out like horrible, right? We randomly initialize it. It is garbage. It is no good. It starts, as soon as it starts getting a little bit better, it starts to notice some patterns like, okay, our generator is currently just spitting out random noise. Clearly, that is just fake. I'm going to look for things that aren't random noise. And our generator's like, okay, well, shit, I got to start generating something that looks like maybe some random edges or textures that look like in our real images. And then the discriminator goes, okay, shoot, now it's generating textures that look about the same. Okay, well now I guess I should look for like high level features. Like, okay, there's texture that looks like a cat's fur, but it's not arranged in a way that looks like a cat. Okay, so I can tell then that this image that has the texture of a cat, but no actual shape to it, clearly it's fake. Okay, now I'm gonna update and say, I'm gonna start looking for shape now. So it starts getting, as they start training, they start one-upping each other. And the hope is that slowly our generator gets fixed. It starts learning to fix all of these problems. Like, okay, I shouldn't output random noise. Okay, I should output something with like shape. Okay, I should output objects that like make sense in the context of other objects in the scene. And so it starts learning to fix itself slowly but surely. And by the loss function here. So the only like loss function that we have to worry about is our discriminator is going to have some, well, we'll talk about this a little bit more a little bit later. But like the basic idea is that like we're going to use the discriminator. The discriminator is classifying whether it thinks the object belongs to the class of real images or the class of fake images. And so the discriminator sort of loss judges both how good the discriminator is doing and how bad the generator is doing. So if the discriminator is classifying, getting a really low like classification loss, it's doing really well, and our generator is doing really shitty. So our generator's score is sort of like the opposite of that. It's like the negative of that, basically. Is sort of like an easy way to like start thinking about it. So like the only loss is just like a classification loss really at the end of our discriminator. Except when we actually go to update our GANs weights, we're going to take the negative of that loss and use that as our loss function for the generator. Does that? It's a little bit nebulous. We'll get to that a little bit later. Yeah, but the loss is really just coming from the end, from the discriminator and how well it's classifying the generator's outputs. So let's see, some little notes here. Why might we need to update the discriminator multiple times as opposed to maybe training the generator multiple times? So the generator only gets better if our discriminator is good. So remember when I said, when I was talking about our generator or our discriminator, if it is looking at an image and it's getting random noise as its fake images, and then clearly like cats and dogs as real images, if our generator is never able to figure out like, okay, this random noise is clearly just like fake images, then our generator is going to have like no clear way. It's going to have no understanding of like how to improve. The generator only improves when the discriminator starts getting a little bit better. and start saying like, okay, if I want to classify this as real, it needs to have some real looking texture, things like that. So it's important that the discriminator is able to actually do its job, because if the discriminator can't do its job, the generator is going to it's never going to get any kind of feedback on how it can improve. So in order to make sure that our generator is doing its job and giving meaningful information to the discriminator about why its images suck, the discriminator may need to be updated a few more times than the generator, so that it can actually discern like a meaningful difference. And this is like a hyperparameter to tune again, like how many times to update your generator or your discriminator for like every single time that you're going to step your generator's weights. So yeah, so like loss functions. So this looks really scary. We're going to break it down here. So ignore like the idea of like expectation, the big E. So let's just go over like some basic terms here. So like V is like our value function, which corresponds to like how much value, like I think it is the discriminator is getting out of this game. X is your input data, just a tensor. Z is just a random vector of noise that our generator is going to use as some kind of like source of randomness. So it's not just generating the same thing every time. D is our discriminator. G is our generator. Okay. So what this ends up being is basically cross entropy loss, which I know we briefly mentioned. It's basically a classification loss. If we are given a set of data that has the label 1 and a set of data that has the label 0, this is simply the classification loss for something which in this case is our discriminator, that has to classify between the classes that are labeled as 0 and the classes that are labeled as 1. Our discriminator's output for a single image is just a scalar, which is why this makes sense if you're interested later in going back and confirming that this math makes sense. So remember, this is a game theory scenario. If the discriminator and the generator have opposite goals, one wants to make this value function really big, one wants to make it extremely small. In this case, the higher the value function, the better the classification. So if the value function is super high, that means the generator is doing its job very well and classifying the images correctly. So the discriminator wants to maximize this value function, whereas the generator has the interest of fooling the discriminator and making this value function as small as possible. And if we're maximizing, in this case, a value function, just note for the discriminator, we're going to do gradient ascent. But this just comes down to like a single keyword in your PyTorch optimizer. Not something to worry too much about. It means just step in the opposite direction from your normal gradient steps. So that is the min-max part of this. Oh, I thought we were going to break this down a little bit more. Yeah, that is the high level takeaway. Probably the most important idea is we have some value function which corresponds to how well the discriminator is classifying. The discriminator wants to maximize its value, and the generator wants the discriminator to suck, meaning it's generating images that to the discriminator look very real, and it wants to pull this value function down. It wants to steal the value from the discriminator. They're competing against one another. So big high-level takeaways. We have two models, a generator and a discriminator. We have a value function that corresponds to negative cross-entropy loss, which is to say it corresponds to classifying very well. Generator wants to minimize it. Discriminator wants to maximize it. They're going to be competing against one another, and we're going to alternate between updating our discriminator and updating our generator, back and forth, back and forth. The generator wins when its data looks real. The discriminator wins when it's able to correctly decide what is real, what is fake. This is sort of the meat of it. So if we want to sit on this for a while and just pepper me with questions, that's totally fine. These are the high level takeaways and probably the most important things from this lecture. So are there questions or comments on this idea of this sort of game that these two networks are playing, and how they can sort of inform each other and progress and get better over time, hopefully generating real looking images at the end. Yes, friend? Yeah. It's like the value. So like we had a loss function to represent like how poorly we're doing. In this case, the value function just represents how good we're doing. It's sort of an arbitrary choice, but the hope is that you understand that with the value function, if you have something like the discriminator, which is trying to maximize your value function, you need to step up the hill and try and get to the top of it. So yeah, it's basically just the opposite of loss. If you're trying to minimize your loss, then the value function is something you're trying to like maximize. It's classification. Yeah, we had a classification loss called the cross entropy loss. And to get the value function, we just literally took the negative of it, which is kind of lazy, but yeah, the paper, they could have simply just formatted it as a loss that the discriminator is trying to minimize and the generator is trying to maximize, but they wanted to be confusing. Or maybe they'd been doing a lot of reinforcement learning in which you try and usually maximize a value function. It's sort of just a choice, but again, core idea, value function is the opposite of a loss. It's something, a quantity you would usually want to maximize. So your discriminator wants to maximize the value function here, its ability to correctly classify. And then the generator obviously is doing its job. If its data looks real and discriminator's like, I don't know what this is. This is real or fake. I don't know. Does that make a little more sense? Yeah. If I confused you with words, please tell me. Yeah. Wait, say it. Yeah. So that was like basically you just pass yeah, so we're gonna like, yeah, you're not gonna update the generator's weights. So we have our generator. Oh, this is only sort of on video. Okay, that's fine. So we have our generator and it outputs an image. And then our discriminator. Oh, it's bad. So, and we also have a batch, we also have a data set of real data over here. Real, fake. So what we're first going to do is we're going to freeze this thing. We're going to freeze our generator. So we're going to freeze all the weights. We're not going to update them with gradient descent. We're going to take a batch of real data and a batch of fake data, right? Just passing in some vector of random noise, just some source of randomness. So we have our batch of real data, our batch of fake data, and we're just going to train the discriminator. We're just going to, just like a normal classification task, just train it a whole bunch. Do like one iteration of gradient descent, sample some more fake images, sample some new real images, pass them both in, you know, to give it new data to work with. Do that a couple of times, like 10 times, say. And then we're going to do the opposite. Then we're going to freeze our discriminator. We can still calculate gradients, even though it's, what I mean frozen, I mean, we're no longer going to update the weights of gradient descent. So then we're going to sample some fake images. We only need the fake images when we're updating the generator. We're going to see how well it does in the discriminator. And we're going to ask the generator, okay, which direction could you step your weights so that given these fake images again, given these, or the same, yes, let's just say given the same fake images again, how could you have generated these images slightly better so that the discriminator thinks, okay, they're a little more real? And you're going to do that just like once, say. That's your like second step. And then you're going to loop back to the top and start training the discriminator again. Does that make a little bit of sense? Yeah, how can I clarify this a little more? Or what have I said that might have been confusing or potentially conflicting? Well, I mean, I was talking about yeah, change the discriminator. Yeah. Yeah. So we've generated a bunch of like random noise, and we're going to feed that to the discriminator. So we get a bunch of fake images. You agree with that, right? Now we're going to feed them to the discriminator, and the discriminator is going to give us like a scalar loss, or in this case, it's going to have like a value function. So I should rewrite this. It's not a loss anymore. It's a value of like how well the discriminator did, like good job, right? And we can actually then take the partial derivative of our value function with respect to our generator's weights, right? Because again, this is like all it's all differentiable, right? It's all just matrix multiplications and like ReLUs and stuff, convolutions. So it's all entirely differentiable. We can do calculus on it. So then we're going to say like, okay, using the partial derivative of our value function with respect to some of our weights that are in here, how can we if we were given the same random noise again, how could we have generated better images? Is basically like what this gradient is. Yeah, because again, like it's all differentiable, right? Like it's multiplications and additions, things that we can take derivatives of. But yeah, as we're calculating gradients, as we're doing back propagation, we're just not going to update anything in the discriminator. Does that make a little more sense? All right.
Oh,
yeah. No, that's good. Keep it coming. Yeah, exactly. Yeah, and the idea is sort of like it's a game, right? Like if our discriminator recognizes like in the bottom right hand corner of our images, let's say, okay, in the bottom right hand corner of our real images, there's a pixel. This is a homework question, so you're in on it, or a quiz question. Say there's like a bottom right pixel here that's red in our real images, and our fake images don't have that. Our discriminator is going to say like, oh, I see this pixel colored entirely red. This must be a real image. Or there's a pixel here that isn't red in the bottom right-hand corner. All the real images have a pixel that's red in the bottom right-hand corner. This one doesn't. It must be fake. The generator is going to clearly learn like, okay, if I had updated my weights, if my weights were such that this pixel was just a little bit redder, the discriminator might have a little more trouble. So it's just sort of this game, like any strategy the discriminator comes up with, like I see that real images tend to do this, whereas the fake images don't have this sort of defining feature. As soon as the generator identifies that feature, as soon as the discriminator, identifies this feature as clearly separating real images from fake images, it is then the generator's job to figure out how to fix that. How to generate a feature that looks like that to fool the discriminator, and sort of this back and forth. That is the main idea. Yeah, it's a game between the two, a zero-sum game between the two of them. Does that make sense to people? How are we feeling about that? All right. So conditional GANs. So we've talked about just if we have like a data set of just numbers, like 7 is one image, and another image, maybe like you've got a 6 or whatever, just digits, right? We've talked about how we would go about generating like realistic looking digits, but what if we want to have like some control over which digit gets generated? Because currently with this setup, if we want to generate an image of like a 7, we would have to just keep feeding it random latent vectors, keep feeding the generator random latent vectors until we get something that looks like a 7. And that's not ideal, especially as you have more and more classes. Like ImageNet is a data set that has 1,000 classes. So do you really want to sit there feeding it random noise until it spits out the right kind of object that you were looking for? Like, no. So conditional GANs is basically the sort of solution for that. So yeah, we have a data set of like random number or different numbers between like 0 to 9 inclusive, 10 classes in total. We don't have agency. We would like to have agency. Basically, the idea is appending to our vector of random noise. We're going to just append on a one-hot vector corresponding to that class. So if we want it to generate a 9, we're going to append on all zeros until the very last digit where we're going to append on a 1. So the question is sort of like, or let me make sure I'm not getting too ahead of myself. Yeah. So the question is like, how do we actually make sure that the generator is incentivized to use this feature? Because right now it has absolutely no incentive to use this information of us telling the generator, like, we wanted you to generate a 9 here. It has absolutely no incentive. But the basic idea with a conditional GAN is we're not just going to give the generator this label. We're also going to give it to the discriminator. And again, this is where the idea of like game theory comes back in a really big way. If the generator generates an image, and it was given this data, it was given this right here. Oh, I should also add, we're going to append on this one hot vector to our real images as well. So if our generator completely ignores this, our discriminator has a strategy now. Since every correct image, every real image comes with a real label, the discriminator has a very real strategy now of simply looking at the label we pass in and asking itself, like, does it correspond to the image in question? All real images will have correct labels. But if we get a fake image with maybe a very convincing looking 6, but it's clearly labeled as a 3, the discriminator has a very real strategy of being able to look at the label and say, like, no, this label doesn't correspond to what's in the actual image, and can clearly identify a fake image as fake or a real image as real. So because the discriminator has this very real strategy of being able to look at this label that previously, until we put the label over here, our generator was able to completely ignore, by making sure that our discriminator has access to it as well. The generator is sort of forced, if it doesn't want to get cornered by this strategy of the discriminator, it's sort of forced to pay attention to this label and realize, okay, the discriminator is going to know that I'm supposed to output a 9. I guess I should output a 9. So the only way for the generator to avoid detection is to make sure that its outputted data actually matches the label. Since all real images will have a correct label. So that's the idea of like a conditional GAN. Are there questions on that? Probably are. Yes, friend. No, it's good. I appreciate it.
So we don't actually like change the output.
Yeah. Are you asking like what the architecture would look like?
Yeah, basically the output.
Yeah, exactly. Sorry, this got a little bit messy. Let's see if I can clean this visual up a little bit. Got a little bit convoluted. Yeah, that's basically it. So the generator took in the label that we asked it to generate an image of, as well as a source of random noise, and it outputs a pair. It outputs an image, and it also outputs this same vector. I don't know what we want to call the vector. Let's L subscript fake, subscript F for fake. So the discriminator takes in the output of the generator, the image, the fake image, IF, as well as the label that the generator was supposed to generate an image for. And the discriminator takes in a data set of images, pairs really, of images with their correct labels. So this is the real image, I subscript R in this case, as well as L subscript R for the real label. So the discriminator always takes in an image as well as a label, and its job is to figure out whether it thinks this pair of image and label looks real or not. And again, like there's a very real strategy. If the discriminator sees that for fake images, the image does not match the label, like it's clearly going to be able to tell real from fake, and the generator will have to fix its shit very quickly.
That's not actually
No. Yeah, this label we gave it to it. Like we chose the label. We picked it ahead of time. And the generator cannot influence this value right here. All it can do is try its best to make the image match the label. Yeah. Are there more questions? All right. We will truck on here. Yeah, this is the last section that's really important. And if we have time, we'll cover the stuff at the end, and you can feel free to look at it on your own. But this is sort of the meat of it that I really want to get to. Let me grab my water here. So there's like there's a couple of kind of glaring problems with this. Or not glaring, some of them are subtle, but there are issues with this, and they're very real issues, and are sort of why GANs are not as popular anymore, compared to much more stable methods. So the generator can stop learning. We need to make sure that the generator is progressively getting better and better. But there's a problem. If the discriminator gets too good, like way too good, like on almost any image, it's almost able with 100% accuracy to classify it as real or fake, the generator has a very real problem. Then in this case, when the discriminator is way too good, there is no direction in which the generator can step its weights to become slightly better. The generator's weights are going to go to 0 if the discriminator is way too good. This can also be thought of in a more theoretical sense of like the discriminator learns super sharp decision boundaries, and lots of flat spots on your loss landscape for the generator. So that is one very real problem. If the discriminator is so good, the generator might have literally no directions in which it can step to better its advantage in the GAN game. The generator can also slip up and get caught in mode collapse. If it finds a set of maybe like 10 outputs that do pretty well, the discriminator is pretty convinced that they're real. The generator might be incentivized to just start outputting those fake examples a lot. But by the time the generator catches on, the discriminator might be sort of stuck in its ways and just perpetually outputting those 10 images, mapping every single source of random noise to the same like 10 images. This is called mode collapse. For any setting of the discriminator's parameters, the generator will always have its value in the GAN game, or its advantage maximized when you output only the one best performing fake. So this is sort of like a weird, to describe this in a slightly more mathy sense, like you can think of like the set of all, I'm going to do it over here so you can't see. Imagine this number line is like the set of all possible images that the generator can output, right? And maybe like this is the score on the corresponding image, right? Or rather, it's a value function that the discriminator or the generator is trying to minimize. So I guess it would be the other way around, but. So this is the value function. On the single lowest example, the single best performing image that the generator could create, the generator's expected value in this GAN game, or the value function in the GAN game, an expectation is minimized when the generator only outputs that one image. Because if the generator outputs a couple of images that are like over here and don't fool the generator as well, then the generator has done worse in the GAN game. The generator is sort of encouraged to just output this one example every single time is sort of the idea. This is called mode collapse. It's not good. And it's definitely an issue. There's also a lot of training procedure issues. So the vanilla GAN setup doesn't converge. Like with our other models that we train, your loss function goes down and it eventually stops improving. But on training data, your loss is, unless you've done something like horribly wrong, your loss is probably just going to go flat, your training loss. So it's gonna converge. It's gonna stop improving. There's gonna no longer be a way for your model to improve on your training data. GANs do not have this. it is a perpetual game, and there will always be slight little edges. The discriminator can always try and overfit to specific features, specific patches of pixels in real images and say like, oh, I've never seen this patch of pixels before, this very specific configuration of pixels. So I'm going to try and overfit to that. There's going to be a perpetual trade-off between your generator and your discriminator. You're never going to have a clear way to look at like a loss function and say like, okay, it's no longer improving. There's no metric to tell you when a GAN is done training. Yeah, it is never going to converge. In our default setup, there's going to be a perpetual trade-off. So these are a whole bunch of different issues with GANs that are like really common, and it's why GANs are really, really annoying to train. They give really good results sometimes, but they can be incredibly fickle. Yeah, are there questions on this? Because this is like something you're going to probably encounter on the homework like at some point, and like you will hopefully, if we've done our job right, you will observe it in at least one context, because it's sort of one of the defining features of GANs is how unstable they can be in like the default setting. Okay. If there aren't any questions on that, we will keep rolling on. But that is sort of the main thing. All of the stuff before now is really the main stuff we want you to take out of this lecture. Everything from here on out, if it goes way over your head, totally fine. It literally does not matter. We're not going to have enough time to cover all of it anyway, which is why, again, if y'all have questions on anything, I can go back to a slide here and we can just hash it out, because everything before now is like far more important than like these little minor improvements that people have found to like make them a little more stable and stuff. Yeah, so people want to like, if there's questions, comments, concerns, points of discussion, before I'll move on, I'm happy to take those first. All right. I will keep trucking then. So the first thing is looking at the actual like math for the loss function that we defined. This improvement would be known as the non-saturating loss. It was proposed in the original GANs paper, but they didn't actually use it for some reason. I'm not sure why they didn't test that one out, but it's basically a simple reformulation of our generator's objective. So beforehand, it was very simple. There was a single value function that our generator was trying to minimize and our discriminator was trying to maximize, just a single value. But now we're going to change that. So the discriminator and the generator are going to have slightly different goals. So the problem with this, if the generator is failing totally, so you can see on the x-axis, it's a little bit small, I apologize. The x-axis is the discriminator's output, whether it thinks an image is real or an image is fake. So just from like the partial derivative of your loss with respect to your discriminator's output of 0 or 1, just this very first derivative, this very first partial derivative, if you look at the case in which the discriminator is not being fooled, the discriminator thinks, okay, this image is fake, it's clearly 0, it's a fake. If you look at the actual slope, like the magnitude of the slope, the magnitude of this partial derivative is incredibly small when the discriminator is just shutting out the generator. So this is kind of a problem that the generator only gets like that first partial derivative, the derivative of the value function with respect to, in this case, it's the discriminator's output on generated data. That first partial derivative is problematically small for your generator when the discriminator clearly recognizes that it's fake. So rather than formulating this right here as our generator's objective, to try and minimize, this is the only term in our value function that our generator has any agency to change. Rather than trying to minimize that, instead we're going to try and minimize something, or maximize rather, something slightly different. It basically boils down to a slight mathematical trick. Rather than minimizing this term in the cross entropy loss, you're going to maximize something that's extremely similar. I don't think I have a good way to explain this, but it ends up being a little mathematical trick. So in the case when the discriminator is absolutely just shutting down your generator, and it's clearly recognizing, okay, it's a fake image, let's classify it as 0. Your generator gets much larger gradients, and it will learn a lot quicker. And sort of helps us out with some of these training instabilities to some degree. Yeah, it's sort of a strange thing. It's basically the way to think about this is, rather than the generator trying to minimize the value function, which is the negative cross entropy loss, let's try and instead just maximize the probability that our generated images get classified as a 1 as real data. It's like this, it's the most minor of tweaks, but it makes a large difference. Rather than just blindly trying to minimize the value function, the negative cross entropy loss, rather than just blindly trying to do that, try and very specifically make it so that your generator's objective is to maximize the probability of getting classified as a 1, using like similarly like a binary cross entropy sort of loss. It's a little bit strange. Don't expect you to get it right away. The idea, though, non-saturating loss will give us larger generator gradients and allow us to train quicker when the discriminator is just shutting down our generator. There's literally no way I have time to get into Wasserstein GANs. So we can just cut it off right there. If you want to, you can peruse this at your leisure, but there won't be quiz questions or like homework questions on it. It's just sort of advanced stuff if y'all want to go into it. So I'll end the recording there, but if y'all want to come up and talk about it, I'm happy to talk more about these advanced kind of GAN training techniques.